I think caching is one of the first concepts or like fundamental things that you start to learn once you start your career, especially if you're a backend developer. And there is something like artistic or like beauty in it. So before we discuss what that is, how many of you have implemented caching? Cool. Uh, and how many of you have seen issues with caching or have implemented a backdoor to invalidate caches? Okay, I was expecting more numbers, but anyway, I think most of us have seen some kind of issues with caches. At least that's my assumption. But so that's the beauty of caching. You start to learn about trade-offs and imperfection of the thing that you are implementing, and that's the first thing you learn at the start of your career. Like you would be coming from college, you would be more deterministic in nature, like learning about maths, computative programming, which is binary in nature. Either correct, wrong. There is no in-between answer. So caching is one such thing where there is an in-between. So that's the beauty of it. Cool. A little bit about myself, like Shraddha already introduced Srinivas, and I started my career at Zomato as a web developer. Eventually transitioned to SRE and led the SRE team there. Now I'm doing my own venture. Cool. Let's start to define like what does like the traditional definition of caching. So like traditionally it is defined as like a high-speed data storage layer, faster than your primary storage, and most often it stores a subset of the data and also transient in nature. And because it's faster, your data is served to whatever is your use case faster than your primary storage layer. But if you have spent enough time with caching as a technique, you would notice that this definition doesn't fit well into a lot of cases where you would call this is a cache in production. So I see two basic lacking items in this definition, which is that most of the time when we store some data on a faster storage layer, that faster storage layer is completely different from your primary storage. So essentially you are storing a transformed copy rather than the original copy of the data. And another thing that is different from or like missing is that the traditional definition is only tracking efficiency from latency standpoint. It is not tracking efficiency on other dimensions at all. Like it assumes that caching system is only for improving latency. But like you would see that a number of caching systems optimize a number of other things as well, like multiple dimensions. So that's what here the definition shows. Like you have the source storage system, which is inefficient on some X dimension, and you are storing a transformed copy onto a storage layer that is efficient on some X dimension. Cool. Let's jump into like what kind of wins we get out of caching, so that it gets clear why that definition makes much more sense. So, like saving vendor API cost. Here you're not saving latency cost, essentially vendor API cost. So, like in Zomato, when you open Zomato app, right, you start to see on the top left the locality where you are in. Like say here it would show Bangalore International Center or HSRA, Kormangala, etc. So how do we get that locality? It essentially fires a API call to Google Maps based on this lat long current location. What is the locality where the user is? But the problem with this API, right? It's really costly, and your users or your locality names are not going to change that frequently. Probably once in 5 years or once in 10 years. So even though you don't care about latency in this regard, you want to optimize the cost of a vendor API. So the dimension your caching system is optimizing is not latency, but a vendor API. Now, saving database cost, like most would use a caching system to optimize the latency of database, but not the database cost. But if you have encountered any databases which are like really highly costly in nature, like for example, DynamoDB is one such database where reads are like insanely costly, more costly than what you would see in Postgres or like MySQL. Different trade-offs, but more costly. So one idea is that even though you don't want to optimize latency, because DynamoDB latency is like very healthy in nature, like 5 to 10 milliseconds, you would want to save the cost by using caching. So again, the dimension you are saving here is the cost dimension. And again, same thing, DynamoDB writes are almost 10x costlier than reads, which means that like almost reading is 10x cheaper than writes. What it means is that like when you have a lot of production systems, you start to see this pattern where a lot of analytics systems, they do a lot of duplicate writes. Easiest example that I would give you is like, let's say driver location of Zomato. He could be standing here for 10 minutes, but you would send pings doing duplicate writes of hundreds of seconds. So rather than doing duplicate writes, you leverage caching. Basically, you read it from the cache. If the location changed, then only update the location. The idea is that here you're trying to optimize the write cost. So here, till now we discussed the dimensions of read cost, vendor cost, and API cost. Now we get to something close to latency. Here we are not actually optimizing the average latency, but we are trying to optimize the latency distribution. So let's take a database like MySQL. Because MySQL offers a lot of features, it internally contains a lot of queues in the implementation layer. So every mutex is essentially a queue that can add your tail, extend your tail latency. So what you see from a database like MySQL is your tail latencies are very, very lengthier in nature. So your P99 could be 500 milliseconds and P95 400, but your P50 is only like 5 milliseconds. So idea is to pick another database layer which has less number of queues. For example, if you were to pick Cassandra, by storing whatever results you are getting in MySQL and storing in Cassandra, your tail latency is reduced significantly because Cassandra is a simple key value database. The number of queues involved in the implementation layer are going to be much, much less. So here, by using Cassandra as a caching layer, what you're trying to optimize is your tail latencies, not your average latency. Because in the end, like on an average, it accesses the disk, so still 5 milliseconds. Cool. Now, like caching is not just for saving some cost dimension or anything. Like sometimes you are improving on, not just reducing, you are improving on resiliency dimension. So let's imagine, like most of us have seen microservices environments, which means that like in microservices, let's take an example of in Zomato, there is a service which essentially tells whether a restaurant is on or off. Cool. All it is saying is all the client services would be calling those restaurants and asking whether this restaurant is on or not. Like it could be powering driver service and number of services. So like let's imagine this microservice of on or off goes down. Now your entire all client microservices don't have an idea whether the restaurant is on or off, which means they have to go with an assumption. Let's assume all restaurants are on, which means your clients will face a lot of dummy orders. So one idea is to implement cache. You cache that on your own service as a fallback cache. You're not going to use this cache until your downstream microservice goes down or you get an error from it. So what you're optimizing here is like being resilient, but not any cost dimension you're not optimizing, or neither the latency. Another way you can improve resiliency is by caching expensive queries. Like most expensive queries are like, they behave differently at different load points. When you have lower load, an expensive query can give you results within a second. But at a higher load, that could be multiple seconds. Alright, I think we saved a lot. Like we saved the vendor cost, we saved on cost dimensions, database cost, latency, and latency distribution. And we achieved a lot, right? But there are always disadvantages. So, so the idea is that the bill always comes to you. Even though you achieve a lot in terms of savings, there would be some kind of compromises you took on knowingly or unknowingly. So let's jump into those parts of the caching system. Cool. So, like intuitively, we would imagine that a caching system reduces latency, right? Now, what if I'll tell you a story like where a microservice introduced a cache, it increased the latency rather than decreasing the latency. So let's set a context here a little bit. So this is a simple get operation. We're getting from the database one item, and its latency is 9 milliseconds. And like databases are like heavily optimized for batch operations. They are so optimized right now that your individual operations and batch operations almost have similar latency. So if you were to fetch one item, it's 9 ms. If you were to fetch 100 ms, 100 items, it wouldn't take more than like 10 or 12 milliseconds. So someone thought like, okay, this is too much latency for us, let's see how to optimize it. Now they check the stats of a different microservice or like same microservice, different stats. A single get operation from a caching system is taking about 1 millisecond. And if you were to fetch 100 items, 2 milliseconds. So the idea is like put the caching layer in front of database and now done. You're optimizing latency. But the key kind of fact in this is that your hit rate, caching system has a hit rate, which means like it has a 99% hit rate, which means out of 100 items, it couldn't find on an average one item. For that one item, you have to go to the database. So what's happening here is that your batch get from the cache is 2 milliseconds, and a single get from database is 9 milliseconds. So overall, you're in total spending 11 milliseconds, which is like 10% higher than what you have spent before when you were batch getting directly from the database. So this is like kind of counterintuitive example where a caching system can introduce additional latency. Cool. So one other story is that a client microservice team added an API timeout and it broke production. So again, let's set some context. Like this all depends on the concept like timeout propagation. The key idea behind timeout propagation is that let's imagine you have two microservices, A and B. Let's say if A is saying that I'm not interested in the request anymore. Now B is thinking like if the client is not interested anymore, why do I have to keep doing the work? That's additional work, right? So the idea is if the client is not interested anymore, I'll stop doing the extra work at the server side. So that's the timeout propagation. Now, so here the microservice A is calling microservice B, and on an average, their average latency across all API endpoints is 5 milliseconds. So they thought, okay, our average response time across all endpoints is 5 milliseconds. Let's put a timeout of 10 milliseconds for all API endpoints. Cool. And they didn't face any errors once they deployed this. But what happened? At some point, a cache got expired. After that, the error rate started increasing. What internally is happening is that, on an average, that endpoint is responding in 2 milliseconds. So here, it made an API request to B. B is internally calling the cache read. So when the cache is available, you are returning within 2 milliseconds, which means it is under the time. But when cache eventually gets expired, based on the expiry stat, it's going to go to the database read. And in the database, it is spending about 10 milliseconds, which means like timeout already triggered. At that point, B thinks that, okay, I'm not interested in the request anymore, I'll cut it off from here on. So it never got the chance to write it into the cache. So every request that is going to B is trying to read it from the cache, getting a mess, doing the work from the database, but never saving that work. So like if you have like 1000 RPM before from caching system, that 1000 RPM suddenly shifted to database. So that's how like adding an API timeout broke production. Not instantly, but like after an hour or two. Cool. So let's talk about like something that's like very common or like core feature or like functionality of a caching system. It is that the caching system or like workflow in general is a very fragile and brittle system. So like in material sciences, a fragile system is something like every kind of material fails, right, beyond certain point. When do you call a system fragile is like beyond a certain threshold, it fails at a very, very high rate. So it explodes. That's a fragile system. So for example, if there is a single button and I click that button and then nuclear bomb blasts, that's a very fragile system. There has to be a lot of checks and balances. To balance out for this much impact, there has to be a counterbalance. So a fragile system doesn't have that. So one way to easily kind of build a mental model is, in this kind of system, you have this happy path and you have a sad path. So your system goes through this happy path 99% of the time, sad path 1% of the time. But these are all, both of these are normal paths. These are not like success and error path. You wouldn't expect error path in a system when you are like building that system. But when you are building a caching system, you expect the sad path, which is that a cache miss can happen. So what makes this system fragile is that the happy path, so every time your system goes through a happy path, you essentially earn 1 rupee. And every time your system goes through sad path, you lose 10 rupees. That kind of uneven difference is what makes this fragile system. So net, you would think after implementing the system, okay, net profit is 90 rupees, it's a good system. But what you're failing to understand is that even if like 5% or 10% traffic shifts from happy path to sad path, right? You essentially go into net loss altogether. So whatever gains you got, you were not getting any gains, just 10% difference. From going from 99 to 90%, you lose that edge. So traditionally, like this is called a bimodal system. Basically, any system that has 2 modes of operations is like a bimodal system. And when a fragile system, when it transitions between the modes, you face cascading outages. Cool. So let's discuss some kind of cases where it becomes apparent why caching is that fragile system and it has multi-modes. So like most of us, when we encounter errors from caching system, let's say timeout from Redis, we treat it as a miss and we take it to the database. But the problem is here, if you treat every cache error as a cache miss, even a 1% transition, right? If your happy path is 99%, 1% is sad path, even 1% traffic from that 99 to 1 means you are increasing essentially 100% load on the database. If your database CPU is like 50%, even 1% change in that is an outage. So how do we solve it? So we want to tolerate the cache errors. So what does the meaning of tolerating cache errors? It means that we selectively choose when a cache error is a cache miss. How do we do that? We essentially set a budget, saying that 5% of the time, or like if my total throughput is like 100 RPM to the cache, I will treat 5 RPM as, which are errors as misses. But if I'm getting 6 RPM as error rate, I'm not going to treat it as a miss anymore. I'm going to treat it as an error. That way my downstream database doesn't get impacted. Cool. Now let's imagine another scenario of, as I mentioned, your one win of caching is caching expensive query results. So what happens when you face a miss on this expensive caching query? So when that happens, like if your caching expensive query latency is 2 seconds, at an off-peak time, it could perform within like let's say 2 seconds and at an RPM of 2 RPM. So even if it is computing, you might see 2 cache misses. Your database will see 2 RPM increase from 0 to 2 RPM. But what happens at peak event, right? that expensive query has a throughput of 100 RPM or 1000 RPM. So if there is a miss at an at a peak event like New Year or like Diwali, your database system gets immediately overwhelmed and you face a cascading outage. So how do we fix it? One thing is sure that we can't fix all expensive queries across the system. We need to figure out a way how to crack that sad path to not show as much impact as it would at a peak event. So there is no traditional solution for this. The best you can do is proactively identify what are those queries that can happen. So how do you do it? You do it by forcefully injecting cache misses at an off-peak time. So you essentially pick an experimental cohort of your traffic, and let's say you pick that 10% traffic as the experimental cohort, and for that 10% of the time, you forcefully increase the cache misses. Like in your program, you can say that even if you're getting an item from the caching system, you say it's a miss, and see how the system behaves. Once you get this data right, you can do a subset difference of the experiment cohort and non-experiment cohort to find out what are those queries that are causing load at a peak event. Subset difference is important because like you have natural traffic also which is the highest load on a database. Cool. So another thing is cache retries. Just like cache errors, whenever you face a timeout, you would want to retry, or like any error like serialization, codec error, things like that. You would want to retry, and when you do that, like on a normal time it might be fine, but when your system is facing, let's say, a blip, essentially you'll suddenly overwhelm your database with a lot of traffic, caching systems. So how do you do that? How do you save from this retry storm? Is same, retry buckets. You say that if your total throughput is 100 RPM, you're going to only entertain retries up to, let's say, 10 RPM. Beyond that, I won't retry it. I'll treat it as an error. Cool. So let's discuss another kind of a boon and bane of a caching system. Cool. So it's about the power law, the nature of caching. Why do we implement caching is that we notice an access pattern on the database where a small number of items have the largest frequency in nature, or like largest load. So the power law looks like this. So we do that caching or layered caching because we identify this insight. So if you see any caching access frequency, you plot the access frequency and you plot cache keys on x-axis, you would see that this kind of power law graph, what it means is that like the starting layer is eligible for another caching layer that you can keep, or not a layer, just another system you can put which has higher efficiency at another extra cost. So this is kind of not new in nature. We learned this in computer systems like hardware. We have L1 cache, L2 cache, and main memory. A similar thing you could implement in these systems as well. Like you basically have a thread local cache, container local cache, and then centralized cache. The idea is in each layer you're trying to put this highest frequently accessed items in a smaller layer that is much more efficient and much more closer. Cool. So now the disadvantage of this access frequency. So even though you are putting that top layer, right, you still have to think that you are still part of that exponential curve. Which means even if your caching system is optimized, your caching system internally would still show that power law graph. Which means your load is not distributed in the nodes. So this can happen in multiple dimensions: compute, memory, and network. If it is compute, what you would see is that some set of keys have the highest throughput in nature. So how do you identify? You can't kind of log every access key. So what you have to do is essentially build a hash map of heap map. You hash it into a smaller slots of heap map and see whether you have a heap graph or not. If you have, then that means that you need to add one more layer to optimize. So if it is memory hot nodes, then you have much less kind of way to fix it. You can snapshot it and see what are those big keys or like keys that are not hashed properly. So network is much harder in nature to detect. So if memory is much easier, like when you have bigger keys or like compute is also easier, what is the highest input keys. But network is more dangerous because you have these like medium-sized keys with medium throughput, like let's say 1 MB and 100 RB. It's not like GBs in nature, but that in itself is contributing to 100 Mbps. So you can build observability on top of it to detect whether this is happening and proactively solve it. By implementing throughput tracking with key clustering, you can use. Yeah, solution is similar to compute. How many of you want to talk more about disadvantages? I don't think so. Cool. I think the video is fine. But anyway, so let's try to generalize what kind of characteristics we observe from the system. The idea is that a lot of times we don't see, nobody is going to name that Cassandra is a cache. Like the idea is to characterize the system proactively so that you identify when systems are not explicitly named this is a cache, you proactively identify them and you apply the failure modes you learned. So like caching system, the key characteristics would be that whenever you see one storage layer optimizing on one X efficiency dimension, right, you can consider that it resembles a caching system. These efficiency dimensions are like, imagine a multi-vector system where you're optimizing one dimension, but you're also increasing in another dimension. If traditionally cache decreases in latency, but increases in cost because we have added another layer. Another thing is that transientness. As I mentioned, cost is one vector that often increases because you're trying to optimize other dimensions, which means if you want to control that cost, you have to introduce transientness. You have to limit how much you are storing in that system. Another thing is durability. You need to be very aware about the durability of your caching system. Like for example, AWS doesn't guarantee durability for Redis. So if one day you lose the cache, you will face an outage. So another thing is source of truth. It's always important to remember that cache is not your source of truth. That will tell you how to recover from incidents or like issues where you are facing invalidation or consistency issues. Cool. I think that's all from my side. So I'll tell you a little bit about what we do. We started out as a cloud cost optimization startup, but we didn't find PMF. But exciting thing is that we are now pivoting. We don't know what to. So if you are facing any problems in platform, SRE, DevOps, anything in that nature, I would love to discuss it with you. See if there is something to solve or like product. Cool. Thank you. Any questions?
So basically, I have just one question. As you discussed about the pin code that long thing right in the beginning. So I just wanted to understand, say in today's world, if we have to do some sort of transition wherein the pin code or the locality that we are talking about is not that much known to Google Maps. So for an example, we are talking about some pin codes which are very far from this locality we are living in, because everything is sorted here in terms of address. Right? So if we have to reach some villages or somewhere at the very far end of the India, for an example, and we have to do the transition. So say there is some sort of things that we need to transfer. I mean, like, it's a coded kind of a situation, right? And we will not have pin codes and everything being located. So how this caching system will behave in today's world? I mean, what would happen?
So here, I think the major thing is that caching is just a layer on top of private system. It's
ಮೈಕೆ ಬರ್ತಾ ಇಲ್ಲ ರೀ ಮೈಕಲ್ಲೇ ಮಾತಾಡ್ತಾ ಇಲ್ಲ ಅವ್ನು ಹೇಳು.
So it will take some time.
ಆಫ್ ಆಗಿರೋದು ಮೈಕ್.
All the system will take some time to do the transition. It would not be easy.
You said we also have to take account of caching outages. So when caching system goes. So when you are planning capacity, do you plan the capacity always thinking that there won't be any cache, or do you do it like thinking that cache will always be there, so this much is sufficient for me? So how do you do that?
So main thing is that caching system is optimizing exponentially, right? It's like if your database cost is 1x, your caching system is helping it come down to 0.01x because caching is 99%. So when you have a system like that, right, you can't provision your main database like to handle the event where your caching system will go. So because it's too costly. Like there are some cases where you can provision systems like that, but they are very few. Like there is this pattern called constant work pattern. But it will be applied in very short quantities. You have to, you can't do capacity planning for an event like caching system can go down. All you can do is like if caching system goes down, how can I recover immediately? How can I make sure that it doesn't transform into a cascade outage? A lot of times what happens is caching system goes down. Even after caching system recovers, your database is now down. You have to work on recovering your database. So the best thing you can do is like how to recover the caching system faster and how to make sure that it doesn't cascade to other outages. Any other questions?
So you always think caching would be there, so you plan capacity.
Like because you can do it, but when you do the math, almost always you would come out to be that you can't handle that much traffic at all.
So you take a hit on reliability basically.
Basically, you need to assume that the combined thing is a single system. You need to just assume that my database itself went down.
But thanks.